Hi, good morning, class. Welcome to the continuation of our lectures on quantum mechanics. And again, I'd like to mention our main reference, which is Introduction to Quantum Mechanics by David J. Griffiths. And if you have extra resources, please, I recommend to buy this book. It's really good for you. It will help you in getting into the details of our lectures. So today for this lecture, we will be generalizing the statistical interpretations of the wave function. So let's start. Let me just adjust something. So we have studied about linear algebra, and we studied the discrete um, linear algebra, and then we applied it to continuous functions. So remember that the wave function is represented by this psi xt. It's a function of position and time. And the wave function has to be normalized. In that case, your psi must be divided by a constant such that when you integrate the square of psi with respect to dx, that would be equal to 1. And of course, the psi should be square integrable so that the integral is finite. That's that's the main condition there. The psi is square integrable, and then you have to normalize it by dividing a constant, because the integral of psi square dx should be equal to 1. So when you have it, so there's a first comment here. The state of a particle is represented by a normalized vector psi in the Hilbert space L2. We know about Hilbert space. The domain of Hilbert space is negative infinity to positive infinity, which contains square integrable functions in that limit. So in classical mechanics, you have position, velocity, momentum, and kinetic energy, for example. And this can be represented by either the position and or the momentum. So in other words, and of course, it can also be, you can also include time there. So um, the the quantities can be a function of, or is a function of, position, momentum, and time. In quantum mechanics, you have operators. So Q becomes an operator in general, but they are functions of X operator, X hat, and the P operator, and of course the time. They are functions of that. But in quantum mechanics, your momentum, this one, is equivalent to that. It has a canonical representation of momentum in quantum mechanics. So if you want to get, and also in the first chapter of this lecture, the expectation value, is calculated by this integral. This one, the expectation value of say for example a quantity q. That's just the integral of psi, and then you have q, the operator q here, and then psi xt dx. And of course, since this is an integral, and you can see that this is just this has an equivalent inner product notation equal to this. So you know about that in the previous lecture. And here q is Hermitian, so that you can put q in any of the phi, or in any of the psi. So for example, here you have psi, cube psi, the inner product of psi and cube psi, and this should be equal to the inner product of psi and cube psi conjugate. And so if you take the conjugate of that, this is just equal to the conjugate. And so in this case, you have you can place q here, and also you can place q here, and they just give the same integral, or the same inner product. In that case, q is a Hermitian operator. So in general, in quantum mechanics, we say that the operator q is represented by is a function of x h bar over i's partial derivative with respect to x and time. So it's not really just simple x pt, function of x pt, but it's a function of the canonical equivalence of x, p, and t. So the inner product is again given by that, and of course you can transfer q to the first side. So so if you have a determinate state, so meaning that when the state does not is exact, when you get the expectation value, if it's exact, then the sigma, or the standard deviation of that q is equal to 0. So if you do this, of course the determinate state would be the expectation value is, or the sigma is equal to 0. So equal to 0 here, and that's equal to sigma, and sigma is just equal to this one. And so writing the expectation value of q, we can write that and then expand that here. So if you look at this, equation here, so whatever you put here, whatever you put in between the brackets, the same should appear here, so that you have this quantity inside the brackets. And then you put that here, this part. And so This is square, but this Q is Hermitian, so any linear combination of that should also be Hermitian. So you can transfer one Q to another, I mean to the other psi. So you can transfer this other quantity here to the other quantity, to the other side, so that you have you will arrive to that, and then this is just equal to this by some uh, postulates before. So this is like the norm. You just square. I mean, that's if you have this a, this is a squared. This is just equal to a a conjugate a, or a conjugate. So this is just what it means there. So now, if you have that, uh, if you have a determinate state, again, the determinate state will give you a standard deviation of 0, and so the only way that this could be 0, the only way that um, the only way that this could be 0 is for the quantity inside to be 0. Hence you have this as 0, and hence you have this. Hence you have this. Only for determinates, determinate variables. That means determine, like the energy of a quantum harmonic oscillator, you have n plus 1/2 h bar omega for the harmonic oscillator, and for the square well you also have um, the energy that is determinate, which is n square pi square h bar square over the width square, no? So this is only true for determinate states. Now let's go to the third comment. Number 3. A measurement of the variable q on a particle in the state psi is certain to return the value lambda if and only if psi is an eigenvector of q with eigenvalue lambda. So this is just the linear algebra that we studied earlier. Now there's an extension to that statement. If you measure an observable q on a particle here, let's read this. If you measure an observable q on a particle in the state psi, you are certain to get one of the eigenvalues of q. The probability of getting the particular value lambda is equal to the absolute square of the lambda component of psi when expressed in orthonormal basis of eigenvectors. But by the way, here there's a statement, but this theorem fails in the infinite dimensional cases, examples of Hermitian operators that have no eigenfunctions at all, or for which the eigenfunctions lie outside the Hilbert space, have been encountered. Because, of course, the eigenvalues of the eigenvalues of the eigenvalues um, of the variables in continuous functions are Dirac delta functions, and they lie outside the Hilbert space. So when we studied about this, linear algebra um, of discrete, what you call this? Say for example, vectors. Those are discrete. Um, we knew that this is you have a if you have a state En or a vector En in or a basis, one of the bases En here. If you operate Q on En, that will give you an eigenvalue, and En should be the eigenvector. So the basis for discrete spectrum. So you have the basis E1, E2 until En. If you choose two different bases, and if you orthonormalize it, this will just be the formula. So if n is m there, if n is equal to m there, that's equal to 1, orthonormalized. But if n is not equal to m, then it would be 0. This is just the meaning of the Kronecker delta. This is 0 if m is not equal to n, and 1 if m is equal to n. So if you take the sum, if you write the wave function in terms of the basis, you use the completeness relation. So this is the completeness relation. So that when you get the inner product or the dot product, you will have Cn here. If you get the inner product of this with En, this one here, you will get the Cn. You will get the Cn here. So this is for a discrete spectrum. And of course, that is the probability of getting the particular eigenvalue. This is the probability of getting a particular value, lambda n. So if you get the Cn squared, you get the square of that. So that's the probability of getting a particular value, lambda n. So now let's go to the continuous spectrum. Because the wave functions are continuous, the same thing follows, except that the eigenvalues are not lying in the Hilbert space because they are Dirac delta functions. So here, if the spectrum is continuous, the eigenfunctions are labeled by continuous variable k. It's still the same equation, but you just have to know that it's continuous. So here, k is not anymore 1, 2, 3, 4, 5, 6, and so on, but it's negative infinity to positive infinity, and they are continuous. The eigenfunctions are not normalizable because they lie outside L2. So look, they satisfy this orthonormality condition. This is a different thing. This is called the Dirac delta, but this one here is called the Kronecker delta. So the Dirac delta has a different definition to the Kronecker delta. So look at this. 399 is different from 3.124. The Dirac delta mean of x is equal to 0 if x, or let's say this k minus l. So it's so the Dirac delta of k minus l is equal to 0 if k is equal to l, and infinity if k is not equal to l. So that's the meaning of that. No, sorry, this is yeah, that's this is if k is not equal to l, and this one uh, wait, if k is not equal to l, and infinity if k is equal to l. So that's the meaning of the Dirac delta, which is completely different from the Kronecker delta. And so your the completeness relation here looks like this. It's the same, similar. It's a similar equation, but you now have an integral because k is a continuous variable instead of the summation, and then you have ck, ek. Look at this. This equation is different because it has summation, because this is a discrete distribution. Now if you want to get ck, then you have to get the inner product of wait get the inner product of ek and psi. So if you square this is just equal to this one, and of course this is if you integrate that, this is the generalized statistical interpretation here. This is just equal to dk if ek is normalized. So let's check if ek is normalized or orthonormal. Yeah, what I mean is orthonormal. So let's say ek or ex prime would be equal to delta x minus x hat minus x prime. So this could only be infinite, or it has only a value when x is equal to x prime. So we'll take a look at this equation here. So you have cx prime is equal to the inner product of ex prime psi. So you have Ex as delta. This is your Ex, Ex prime, and of course Ex prime X, and you have a psi here. And the integral of this, when you have a delta Dirac delta function inside the integral, would just give you the same function, only that you have to use the value of x that will make the argument in the Dirac delta function 0. So in this case, what makes this 0 is when x is equal to x prime. So you have to use x prime here. So now you can see that this is just the probability of finding the particle in the range dx prime about x prime. So we knew this because we encountered this already in chapter 1. So for momentum, the orthonormal eigenfunctions are this. For position, the orthonormal eigenfunctions are this one. For position, we have encountered that in the previous lecture, and for momentum, the orthonormal eigenfunctions are this one. So if we get the statistical interpretation of the psi as a function of the momentum and time, we can also do that. So again, the p, because this is now continuous, would range from negative infinity to positive infinity, so that your component of psi, or the p component of psi, would be would be this. Well, this is the original definition. Then you just substitute EP here. Then you get phi PT here. This is the new, or which is the new function that's now a function of momentum and time. Well, you started originally with psi xt. So if you square this, this is just equal to CP square. So that of course that is that is just the same as this here. So this is by the way, you have dp, here. So you get the integral and then the integral. That would be the probability of getting the momentum in the range dp. So this should be also equal to, from negative infinity to positive infinity, should be equal to 1. So you will have problems here that you are going to try when you have when you have your free time. So take a look at those problems. By the way, the assessment, I will post the assessment for the lectures later today, so you can check that out in our Google Classroom and in our Mole Classroom. You also have this problem. Now we go to the uncertainty principle. We will derive the uncertainty principle. We know that uncertainty principle was, I mean, discussed um, in the second, I mean, in the first chapter, but it was not uh, proved. But here we will prove the uncertainty principle. The uncertainty principle is that you can measure the x variable, but it gives you, but you cannot measure with certainty the momentum variable. Or if you can measure with certainty or with higher certainty the momentum, then you cannot measure then you can only measure the x with very low certainty. That is given by this expression here. That the standard deviation of x times the standard deviation of p is always greater than h bar over 2. So, proof of the generalized uncertainty principle. So, you have the standard deviation is given by this. This is, of course, true. So, if you have a variable a or an observable a, you get the standard deviation of that by doing this. And then you say it's just a inner product of two functions f, where of course f is equal to this. And then also for another observable b, a could be position and b could be momentum, or any other variable that you can think of. So for an observable b, you have this standard deviation. So here, well, they're just the same. Only that you have two different functions for two different variables, and g is of course just like that. G is just b hat minus the expectation of b times psi. So if you multiply that, if you multiply this two, the square, then you will have this. This just the square here, and sigma. So of course, by Schwarz inequality, this product, Schwarz inequality, we studied in few lectures before this. So this is always greater than this one here. Look, when you have a complex number, the complex number is written as z x plus iy, for example, and z equals x minus iy. This is the x is the real part, and or this is the real part of z, and then y is the real part of if the is the imaginary part, I mean y is the imaginary part of z. So if you square z, this is just x square plus y square, z square. So this is just square of the real plus square of the imaginary. And this is always greater than, this is always greater than the square of the imaginary. So you have you have uh you have this you have this equation. I mean, so you finally have your I, the imaginary part of z square is equal to 1 over 2i z minus z star square. Of course, you have by the way, sorry, this is z star, the conjugate. And so that your z minus z star is equal to um, is equal to 2 wait 2iy, so that your imaginary part, this one imaginary part, will be, this will be equal to z minus z star divided by 2i. So this one, that's that one. So now we let z, uh, to continue with the solution, we let z equal to this, we let z equal to that, and then so if this is your z, then your sigma a square times sigma b square would be greater than this one, would be greater than this one here. And so if you compute fg, by the way, f is just equal to if you by the way, we look at f and g first before we continue. F and g, f is just this one, f is just this one, and g is just this one. So you can get the inner product of those two, and here fg. So if you do that, you just manipulate algebraically, although you have to 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 manipulate these operators. You have to operate these operators, and then you just then you will arrive to this. You will arrive to this. So anyway, we'll continue. Um, you have now now you have GF would be equal to this. And so if you get the difference, if you get the difference between FG and the inner product of F and G and the inner product of G and F, you will get this finally, this one. So that this one is the commutation relation. This can be written in this form. Yeah, here, this one here, the commutator of two operators. So that your uncertainty principle in general form is this one. Now suppose we take the operator or the observable to be, or the A hat to be the position x here, and the second to be the momentum B, so that we can calculate this. Since these are operators, we need an arbitrary test function f, and we'll just cancel that when we arrive to the final answer. So here you have x times this is x, and this is the momentum. You multiply that to f, and of course you have h bar over I, this is the momentum, and then you have x. Now you have to operate the momentum here, and here you can only operate the momentum on f. So that what happens is this is h bar over I, which is constant here. You can take them out, so you have x df of dx minus the derivative of xf with respect to x is just equal to x df of dx. So this one will cancel, and so you're left with negative f h over I. If you transfer I to the numerator, that will become positive, so you will have this one. So you now can cancel. F, cancel f. So your commutator of x and p just equal to IH bar. So you will have the uncertainty principle to be equal to this. So your sigma x, sigma p is greater than h bar over 2. This is your this is your uncertainty principle for momentum and position. So there are problems here that you can calculate the uncertainty principle. Say for example um, the variable x and h here. You can also do the, problem 3.40. It would be easy, but it's very long. And if you have so much time, you can also solve this. This is the commutator of x to the n p n p. So that if you have here in general, if you have a function here, f of x, that would just give you ih bar f prime x of f of x. So that's 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 it. So let's now go to the minimum uncertainty wave bucket. So first we generalize the statistical interpretation, then we derive the uncertainty principle in its general form. Now we will go to minimum uncertainty wave bucket. So there are wave functions that hit the position momentum uncertainty limit, which is this. This is the limit. That's the smallest. Um, that's the smallest product of two standard deviations, because the standard deviation, the product there is greater or equal. So the ground state of the harmonic oscillator and the Gaussian wave bucket for the free particle, we take a look at this. So now let's ask this question: what is the most general minimum uncertainty wave bucket? So by Schwarz, this is just an explanation. So anyway, you have if you have two so consider a function, for example a vector or vector function g and f, and if one is a multiple of the other, you have this expression here. Of course there's a ket notation there. So if one is a multiple of that, you can write this to be the real part of the inner product of G is just the real part of C times the real product of F to itself, and this is equal to 0. When you um, when you when you set the equality of this equation, wait, it's still far from here. So when you set the equality of of this complex number z, then you have to set this to 0, so that only the real part is present. So What I mean to say is that only the real part of the inner product of f and g is present. I mean, um, the real part of so I was lost, totally lost. But the real part is zero. You only have the imaginary part present. So you have this. You have this. So you have this result here. You have this result. So finally, you have written that G. You have G equal to CF, but you found out that the C there is just the complex part. So you have to put an I, and then A here will just be any positive constant or a real number. Not positive constant, but a real number, sorry. So when you get P minus expectation value of P, or the momentum, this is just equal to I A x minus x psi, so that so that your psi will have this form. So that's the minimum uncertainty wave packet of for this minimum uncertainty wave packet means that your sigma x and sigma p is equal to h bar over 2, not greater or equal. So there's a problem here which you can solve. This one here. Solve for solve equation 3.144 for psi. Note that x and p are constants as far as x is concerned. So you have to solve this one in order to get this one here. So these are constants because these are expectation values. They're already average values. But of course, x is not a constant, but p, the expectation value of p and the expectation value of x are constants. The energy time, we will now go to the energy time uncertainty principle. Here this is true. We know that this is true. And in modern physics, we also encounter this. And we use this in modern physics. This is true in modern physics. We use both of this in modern physics. But we know that x, the delta x here is standard deviation of x. Delta p is standard deviation of the momentum, and is the standard deviation of the energy. But how about delta t? Is there a standard deviation of time? In relativistic scenario, there is a standard deviation of time. But in classical scenario, time is just only time. It doesn't have a standard deviation. So there's a note here that I will read to you. In here, in relativistic theory, equation 3.147 would be a necessary concomitant or a necessary pair to equation 3.146. However, the Schrodinger equation, which is explicitly non-relativistic, treats t and x on a very unequal footing. As a differential equation, it is first order in t but second order in x. Look at the Schrodinger equation. Um, the Schrodinger equation was like partial of psi with respect to t is equal to h bar over I, h bar over 2m, partial square of psi with respect to x square is equal plus v psi. So this is the psi here is just first order derivative of t, while it is equal to the second order partial derivative of x. But this scenario, this Schrodinger equation is only applicable to non-relativistic scenario. So position and momentum and energy are all dynamical variables measurable characteristics of the system at any given time, but time is not a dynamical variable in non-relativistic theory. Time is not a dynamical variable in non-relativistic theory. Time of a particle cannot be measured unlike its position or its energy. Time is independent variable of which the dynamical quantities are functions of. So anyway, this is just to show that the solution here. So anyway, let's go through the solution. You have any dynamical variable q. You take the time derivative of that. Uh, the time derivative of the expectation value. This could be position, momentum, or whatever. In general, we just say variable q. Then you have this is the expectation value, so that you can write that like this, and then you distribute the time. Of course, it becomes a partial derivative with respect to time because psi is a function of x and t. So that you have that, and then you also have this and this one. But what is so anyway, let's we have the Schrodinger equation here. So if we say that this is if q and h are equal, so you can replace h here, h and h, if you get the derivative of the expectation value of h. This is the Schrodinger equation here. So you can, with this Schrodinger equation, you can replace this quantity by this is now equal to uh, I over h bar h psi. You can replace um, these quantities by this by the Schrodinger equation, and so you will have this. You will have this. But of course, the h here, the energy or the or the Hamiltonian is Hermitian, so you can write this as uh, here. You can write this as that one. You can transfer this one here so that you will have um, so that you will have let's so that you will have this as equal to negative I and 1 over I h bar psi h bar q psi plus 1 over I h bar psi q h bar psi plus expectation value of q with respect to time, so that you will have this. So that you will have this one here. This is just a proof. So in most cases q is in most cases q commutes with h, because h here um, wait, let's go back. Okay, so if the two commutes, if h hat and q hat commutes, then this would be 0, and of course your derivative of q, of the expectation of q, would just be equal to the derivative of q, the expectation value of the partial derivative of q with respect to time. So that's that. So if you do this, you pick the h and q as your variables observable a and b, going back to the uncertainty generalized uncertainty equation, or generalized uncertainty principle. You have this, so that this one is h so your a will be replaced by h hat, and your b is replaced by q hat. So you will have 1 over 2 I h bar over I d of q, because your 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 partial of q hat over time here is, this is 0. So this is h bar square over 2 with this one here, the derivative of expectation of q with respect to time, so that your sigma h sigma q will have this. So your delta t would be this. And so if your delta t is that, then if you substitute to what is E, by the way? E, and the delta E is what? Delta E would just be you can get delta E by let's look at this. So anyway, let's just by setting your delta t to be equal to that quantity that we just derived, we can formulate the uncertainty principle. So anyway, this one, the delta t is given by this, or given by this. So your energy time uncertainty principle would be of course given by this. So delta t represents the amount of time it takes the expectation value of q to change by 1 standard deviation. Look at the standard deviation here. And also there's a note here. If delta E is small, then the rate of change of all observable must be gradual. I mean, you have a lot of time consumed if delta E is small. So if the change is so rapid, then the energy is large. So we'll go to an example to show in order to use that uncertainty principle. In the extreme case of stationary state for which the energy is uniquely determined, all expectation values are constant in time. As in fact, we noticed some time ago, equation 2.8 in chapter 2, to make things happen, you must make a linear combination of at least two stationary states. For example, this one, linear combination of two states. So if you get the square of that, there's a bar here, a vertical bar. This would just be this one. The time oscillation, the period of oscillation is just equal to uh, this here. It's equal to this, the reciprocal of this. So that's this one, and then your, of course, delta E would be yeah, the delta E would be here, the difference of energy between E2 and E1. So if you multiply delta E with delta T, this is just equal to 2 pi. By the way, this is equal to um, 2 pi h bar over delta E times delta E. You can cancel this delta E. So you will have 2 pi h bar, which is greater than h bar over 2. So it follows the uncertainty principle. Example number 2. How long does it take a free particle wave packet to pass by a particular point? How long? How long does it take? How long does it take a free particle wave packet to pass by a particular point? So we can do this, no? Say, what is V? V is equal to delta x over delta t. So that your delta t is equal to delta x over v. And what is delta x over v? So if you multiply this delta t with max over mv, this mv is your momentum. So your delta t would be this one, max over p. And of course, energy also is equal to E p squared over 2m. So if you get a small, it's just like derivative. If you get delta E would just be the derivative of E. So delta E would be equal to derivative with respect to P. This is 2p dp, which is also delta P over 2m. Cancel. So you have delta, or you have P delta P over m for your energy. And so you can derive delta x delta p greater than h bar over 2, because this is greater than x bar over 2, h bar over 2. Example number 3. The delta particle lasts about 10 to the 23 seconds before spontaneously disintegrating. If you make a histogram of all measurements of its mass, you get a kind of bell-shaped curve centered at 1232 mega electron volts per c squared, with a width of 115 MeV over c squared. Why does the rest energy mc sometimes come out higher than 1232 and sometimes lower? Is this experimental error? Of course, it comes out higher or lower because of the uncertainty principle. And is this an experimental error? No. The answer is no. So here you have uncertainty principle. Um, this is the width of the particle delta. The width of the particle delta here. Here. And the time is 10.23. So if you calculate that, why do you divide this by 2? Because it's a width. Because it's like the width at half maximum. So you have to divide it by 2. So your delta E, delta T would be this would be this, and this one is greater than um, of course h bar over 2, and so it follows the uncertainty principle. So we notice that in example 1, time t is a period of oscillation. In example 2, the time is the one that it takes a particle to pass a point, or the decay time. And yeah, in example number 3, the lifetime of a particle, so the decay time, or the time it takes to pass a point, or the period of oscillation, this one. So that ends the chapter. You can check the problems here. I'll just give you time to screenshot them, and then in your free time you can solve them. I will post later the assessment for this lecture so that um, you'll be able to do your work on the weekend, or if, but the deadline of that would be next week, or I'll just announce if it's going to be next week. You have this problem, and then you also have this problem. You also have the continuation of that, and then here these are a long list of problems which you can spend time on to learn quantum mechanics. Just review the lecture, and then you'll finally understand why. So I think this is already the last page. We have finished chapter 3, and then we will now no in the next lecture we'll proceed with chapter 4. So it's gonna be three-dimensional wave function. So see you next lecture, and then we will do Schrodinger equation in 3 dimension, and then we will apply those to physical system like the hydrogen atom, for example. So we'll talk more about that in the next chapter. So see you, and I will post the assessment uh, later today. Just wait for it.